He was the interviewer was in the Navy.
Okay, how's everyone doing today? Y'all doing good? Y'all ready? Has anyone, well, I know some people have started working on that take-home. Going okay? You answered my question with a question.
I don't think it was a question. I said it was more of a statement.
Give us the answers.
That's usually how a professor answers.
Okay. Let's begin. If I can find this thing, there it is. So we were almost done with 11.2 last time. We had pretty much determined that when it comes to surfaces, functions of two variables, that it is very difficult to find the limits. And that the only real good technique we have is the squeeze theorem. And I did a problem where we used the squeeze theorem. And then the last topic of this section is the idea of continuity. So remember back in Calculus 1, for a function to be continuous at a point, so let's say we have some function, we have some point A here. To say that this function is continuous at A meant that not only does the limit from the left exist and the limit from the right exist, but that limit as x approached A of the function was equal to the function's value at A. So you couldn't have a hole here, it had to be filled in. And that's what it meant to be continuous at A. And we have a similar definition of continuity for functions of two variables. We say that a function of two variables is continuous at the point AB, which is a point on the plane, if the limit as y approaches AB of that function of two variables is equal to the function's value there. So the way to see this would be if we've got some surface, okay, and remember the ground down here is where the point AB is. That's the domain down on the ground. That point gets plugged into the function, and you get this point up on that surface, right? To be continuous means that the limit exists and it's equal to the function's value there. So as you approach that point on the surface from any path, the limit exists and it's equal to the function's value there. So you don't have a hole in that surface. You see the similarity here? Any questions on that? Okay. Now, we know it's going to be really difficult for us to ever figure out if a function is continuous because we know that limit's hard to do, right? So what we have is a very nice result, and that's this last note here for this section. And it says that all polynomial functions f of x, y are continuous everywhere on the entire two-dimensional plane. That means if your function of two variables is a polynomial, has x's and y's raised to various powers, that's a polynomial function in x and y. It is continuous everywhere. You're not going to have any jumps, breaks, gaps, holes. It's all good. All right? You don't have to prove it. It's just understood that it's continuous. Also, all rational functions are continuous on their implied domains. So we talked about domains last time. Domains of functions of two variables. If it's a rational function, that means you have a ratio of two polynomial functions, then it's continuous as long as the denominator can't be 0. And then lastly, the composition of continuous functions are continuous on their implied domain. So if you take a continuous function, plug it into a continuous function, you still maintain the continuity. All right, that's it. We're done with 11.2. We're going to move to 11.3, partial derivatives. All right, so I've got a pretty good little picture here to show you. to help you understand what a partial derivative is. But we'll begin by remembering from Calculus 1 that the derivative of a function of one variable represented the slope of the tangent line at a point. So if I have some function, the slope of that red line is the derivative of that function at some point. So, here it looks like at about -2. Yeah, look, I'm right at it, -2. Looks like at -2, when we plug that into the function and we figure out the derivative at -2, we get this red line, and the slope of that red line is -4. Right? So that's what the derivative produced for us, the slope of that tangent line. The problem that we're going to encounter here with functions of several variables, like a function of two variables, is that we have two variables, first of all, right? This makes determining a single tangent line somewhat difficult. So what we're going to do is take a look at a graph here. All right, I'm going to make this a little bit bigger. All right. All right, can you all see this surface? Does that kind of help? You see it? Okay. So we've got this point on the surface. Now I can move that point around a little bit so you can see it moving on the surface. Oh, where'd it go? Oh, picking the wrong thing there. Bring it this way. Okay, so if we're looking at this point, then does it make sense to talk about a tangent line? What would be your, I guess if you're going to scratch your head about that question, what is it that's causing the issue? Yeah, like which way am I pointing, right? Like which way is that line pointing? When we were in Cal 1 and we had a function like this, then it was very natural for us to just put a line right, at the tangent just like this. But if we have a surface, there's an infinite number of lines that go through that point. It's just like what direction do we point in?
Would all those tangent lines, like to the wall, would that be a plane?
We can make, so I think what you could say is the tangent plane makes more sense than a tangent line, right? A tangent plane makes more sense than a tangent line. A simpler way to think about it is, let's say you have like a basketball, right? And if I have a basketball here, I could of course go to the North Pole and place a line on top, couldn't I? But I could spin that line around and any of those lines would actually be tangent kind of, right? And if I go to any point on that ball, right, I can do the same thing and spin a line around. So instead, take that ball and put a plane on top. I did bring a plane. Look at that, I brought a plane today. So if we take that same ball and we place this on the North Pole and then move that around, a tangent plane seems more natural, doesn't it? And for a tangent plane, what do we need for a plane? 3 points. And what did we do with those 3 points? We got 2 vectors out of it, right? And then we crossed those to get a normal. So would you agree with me that to have a plane, we really just need 2 vectors on this plane? And then from that I can get the normal, right? So if I have a plane, if I can just come up with 2 vectors, then I pretty much have defined this plane. I would also need a point, wouldn't I? But 2 vectors and a point would be enough for me to define a plane. So yeah, I think a plane is more the direction we want to go into, right? So what we're going to do is we're going to do this, all right? But we're going to need to get 2 vectors. And so we're actually going to try and get 2 tangent lines off of this thing. And from those 2 tangent lines, we're going to create the plane. All right, that'll be the next section. 11.4 is tangent planes. This is just partial derivatives. All right, let me see what I say next here. All right, so going back here, let's do this. Check my x and y coordinates here. Let me move my x coordinate to 0, and let me move my y coordinate. Well, that's not working. I'll move it to 0 also. Is it letting me? There's 0. Let me just turn this so you can see it. There it is. Everyone see that point okay? Stop moving. Trying to make this thing bigger. Oh well. There we go. I think every time I move it, it gets smaller again. All right. So let's try something. Right now, my x and y coordinates, my x and my y that I'm plugging into this function are 0 and 0. So down on the ground at 0, 0, I'm plugging that in, and it's spitting out this point, all right? And if you, let me see if it shows the value here. What the hell? Why is it not? Do I have to do this first? Okay. Not sure why that checkbox not working. Was it working in my office today? All right, we're at the point 0, 0 is being plugged in, right? And this is the actual function, just if you wanted to know what that surface was. This is the function of two variables, so we're plugging 0, 0 in. It's spitting out an answer, all right? So let's do this. Let's fix y to be equal to 0. So right now, I'm going to fix y to be equal to 0. And I just want to talk about what that means. If I say to you right now, y is 0, what does y equals 0 look like in three-dimensional space? It's the xz plane, isn't it? Y equals 0 is the xz plane. So imagine coming in here right now, fixing my y value at 0, and that basically comes in and cuts my surface with the xz plane. Y'all see that? Now if I change that value of y and make that y value maybe 1 instead, then that's still a plane that is parallel to the xz plane. So did you see it move out a little bit there? I don't know if y'all noticed it when I moved it. Let me move it back. See it moving? Okay. So all I'm doing is sliding that plane back and forth. So I fixed it back at 0. If I fix it back at 0, can you see that where it intersects my surface, I have a curve? Okay, and to help us see that, I'm gonna actually pull the surface out of the picture completely, so you can just see that intersection. And now imagine that we walk down the y-axis, all right? And I'm actually going to go, this is the positive y direction, this is the negative y direction, agreed? This is the positive x, and this is the positive z. I'm going to go walk down the negative y direction way out, okay? So I'm going to walk out way out to infinity, negative infinity. I'm going to turn around and look back. And when I turn around and look back, here's what I'll see. When I look back, don't I see the x-axis like this and the z-axis like this? And this now is just a curve in two-dimensional space, just like Cal 1, isn't it? And it makes perfect sense, hopefully to you, for me to talk about the slope of that tangent line, right? And I should be able to find that. So what I need to do to figure that out, that slope, is first fix my y to be equal to 0. Y'all with me? That's what a partial derivative is. You're going to basically cheat a little bit by holding one of the variables to be constant, which slices your surface in one direction, and then where it slices, you take a look at that curve by itself. I'm going to go back, look at our normal view. I'm going to bring that surface back in. And let me move that y value out. Let's move it to y equals 1 point. Let's go to y equals 2. Now let's pull that surface out again. And let's go walk out that y-axis to negative infinity, turn around, take a look. That's a different curve, right? Yes. So as I change the value of y and I move it and fix it, it's going to change the curve, and I'm going to have a different derivative for every different value of y. Understand? Okay. So when we fix the value of y, we are letting our x variable still be a variable. And by doing that, it draws the curve. If we fix them both at the same time, then we're just at a point. But by fixing one and letting the other one be free, we have a curve. All right, now I decided to fix the y value at 0, right? That's what I did. But I could have done the x value at 0, couldn't I? I mean, there's nothing stopping me. So let me go back to 0, 0 again. There's that point that we were looking at. And this time, I'm going to fix x to be 0. And when I fix x to be 0, this is the yz plane. So I'm going to cut through this with the yz plane now. Right? And I'll bring the other one up. This was the other one we just did. Notice that those two planes are, ooh, that doesn't look orthogonal, but they are. It's just, that's just a perspective thing. Those two planes are orthogonal to each other, but that just gives you an idea. I'm slicing it in a different direction, right? And then which way should I walk out to look at this? I should walk out the x-axis. Which way? Positive? And look back, or negative? When I look back, okay, when I look back, what I want to see is z and y, z positive and y positive, right? So which way should I walk out? X positive infinity. Walk out, turn around, take a look back, and I should see that, but wait a minute, that surface is in the way. Let me pull the surface out. There's your curve, right? And then let me show you the slope of that tangent line. Now look, if I change the value of x right now, what's going to happen? Wait, sorry, I fixed x at 0, didn't I? I can't change the value of x. If I change the value of y, what's going to happen? I should, let me close this one. Let me close that one. If I change the value of y, what's going to happen? It's going to just move this along the curve, right? That's all that's going to happen. What happens if I change the x value, though? The curve's going to change, because I'm going to be on a different place, a different slice of the surface. So let me just do that so you can see it. Look at the curve changing, right? Can you see that I don't know if you can visualize, it's that plane being slid through the surface. We fix the x to be 0, we allow y to be a variable, and we're back to Cal 1. We do it the other way. Same thing, walk out. Do y'all know now why I walked out y negative infinity? So when I turned around and looked, I saw z up and x positive on the right side. If I would have walked out y positive infinity, I would have looked back and seen x positive this way and z positive this way, which we could do, but it's just not what we're used to seeing. Okay, so if I fix y, tell me again, if I fix y, and I look at that from way out at negative y is negative infinity, and I change x, I'm going to move along the curve, right? Yes. If I change y, I'm actually going to change the curve itself. Does this make sense visually, what the partial derivative is? All right, good. That's right. It's not. There is something called a total derivative. I'm trying to remember where I took total derivatives. I can't remember when I learned that, actually. But there is something called a total derivative where you treat everything like a variable and you get this thing called a total derivative. Anyway. You're never fixing anything. Like nothing is ever held constant. All right, to determine the derivative, at some point we will need to hold either x or y constant. Okay? So in order to find the slope of that tangent line, we need to hold x or y constant. I want to go back to that picture for a second. Let's go back to this. Right now I am holding y constant. Can you all see that from here? Fix the y value. I'm holding y constant. So I'm getting the slope of this tangent line. If I bring the x value and hold it constant, I slice it the other way, and I can bring in that tangent line. And do you see that those two tangent lines together are going to help me generate that plane? Yeah? Okay. I guess my question to you is, are those the only tangent lines that I could have picked?
No.
I could have picked two other tangent lines, right? And that's coming later, all right? There's another type of derivative that we use later on in a different chapter. And we're going to get another formula for tangent planes. But what it allows us to do is, it's called the gradient vector. You walk to a point on the surface, okay? So like that point right there. And then instead of forcing yourself to hold, in this case, y constant. See, when you hold y constant, it forces you to kind of look down a certain plane only, right? So it kind of forces me to point my head in that direction and say, hey, what's the slope in that direction? Later on, this thing called the gradient vector says, hey, go out to the point, and then you decide which way you want to point. And it does not have to be parallel to the xz plane. It doesn't have to be parallel to the yz plane. Just any direction you want. And then just take a step out in that direction, and we can calculate the rise or the fall in that direction. That's called the gradient vector. So we will be able to free ourselves from pointing in two directions only later. Does that make sense or not? Okay. For now, we don't worry about it. All right, so given some function, z is some function of two variables, x and y. If we hold y constant, then we call the derivative the partial derivative with respect to x. If you hold y constant, it's called the partial derivative with respect to x. Look at it this way. What's still free in the problem? If you hold y constant, what's still free? The x. So it's the partial derivative with respect to x. You're still treating this as a function of x. And here's how we denote it. Here's the notation that we use. See, this no longer makes sense. You know, we use that in Cal 1, right? But you cannot, this is bad notation. This is really bad notation because this is saying take the derivative of this, right? But it's not telling me what to hold constant. It just says take derivative. And this is just terrible. So what we have to do is this. We use the subscript of the x right there. That tells you that you're going to hold y constant and treat x like the variable. And then similarly, if you decide to hold the x constant, then we call it the partial derivative with respect to y, and we denote it with this, f subscript y xy. No primes. Nope. No primes.
Is that the, because I've had differentials, so is that the notation that we're going to have to use, or can we use the
I'm going to bring up in just a second all the different notations that you could possibly see. And I'll use this notation. That's the one that I will use. All right, so we're just going to practice here. So the first one we want to find, how do you say that? Find the partial derivative with respect to x at the point 2, 1. Okay, so that means I'm going out to this point 2, 1, plugging it into this surface, going up to the point, standing there, cutting it with a plane, right? That plane I'm cutting it with is parallel to what plane? What am I holding constant? I'm holding y constant, right? So if I'm holding y constant, that plane is parallel to the xz plane. Good. Right? To the xz. It's parallel. And I'm creating that curve, and I'm trying to find the slope of the tangent line in that direction. But we need to know mechanically how do we take partials. So I'm going to first take the derivative with respect to x of the function. Now the way I'm going to do this is just, look, this is one of those things like light bulb. It goes off, you understand it. When you understand it, things go well. When it doesn't make sense, you're going to sit there and like scratch your head forever, all right?
So if it's f of x, y is the constant, right?
I basically want you to look at this right here and act like y is a constant. So y cubed is a constant. And the derivative of a constant is 0. So, pardon?
Do we pick like the y value?
You're not picking the y value.
It doesn't matter because the derivative is just 0.
That the derivative, yes, exactly. And even if, well, we're going to see it in here, the y is going to play a role in here. But then later on, you can plug in the y. Okay? All right, so 0 and then plus. Now I'm taking the derivative of 2x by itself with respect to x, which is just 2. And then plus, now what do I have going on here? X squared times y to the 5th.
So you're going to have 2x, y to the 5th.
Okay, so you might want to look at that right now as a product rule. But that's not as efficient because isn't y to the 5th just a constant?
Yes.
So if that's a constant, when we take derivatives and we have constants attached to functions, we just ignore them and bring them along for the answer.
Yes.
Right? Like if you're doing like derivative of 4 sine x. You can ignore the 4 and just say derivative of sine is cosine and just bring the 4 down. We're going to do the same thing here. Y to the 5th is attached to this with multiplication, so I'm just going to ignore it. Derivative of 2x, of x squared is 2x, right? So I have 2x times y to the 5th, not 0, right? Because it's a constant attached. So 2 what? X, y to the 5th.
Plus 0.
And then plus 0, because the derivative of 10 is 0. That make sense? Yes?
What's the actual notation for a partial derivative?
What's the actual notation for partial derivative?
You know how you have d over dx for a partial?
I'm getting to it.
Okay.
This is the actual notation for a partial derivative. But there's like 5 equivalent ways. You know, I mean, it's like if I write y equals f of x back in Cal 1, and I write f prime of x, everyone knows what I'm talking about. If I write y prime, everyone knows what I'm talking about. If I write dy dx, everyone knows what I'm talking about. These are all different notations, right? Well, this is the notation I'm introducing the partial derivative to you with. But I'm going to show you equivalent forms in just a minute. I mean, like it's coming. It's coming. Because if you're taking differential equations, it's a different notation. Okay. All right, that's our partial derivative with respect to x. Now we want it at 2, 1. So just plug in 2 for x and 1 for y. So 2 plus 2 times 2 times 1 to the 5th. And that's just what, 6? So that means if we were to actually go and plug 2, 1 into this function, and that takes us to some point on the surface, and then we imagine cutting it with a plane, and that kind of creates this curve that we're now standing on. That curve would be running parallel to the xz plane. And if I start walking, and I'd have to be walking in the direction of positive x. Okay, if I start walking in that direction, I'm going to have a slope of 6. So it's going to be rising. Now what happens if I walk backwards, though? It's going to be going down. So I hope that makes sense. All right, now, partial with respect to y. Let's see how that changes. I'll just do that right here. Change this to a little y here. So the partial with respect to y. Now we're holding x to be the constant. So what's the derivative of y cubed? 3y squared. And then the derivative of 2x? 0. And now derivative of x squared times y to the 5th.
5x squared.
5x squared y to the 4th, and then plus 0 again. So here on the x squared, since x is a constant, x squared is a constant. It's just going to come for the ride. But then I have to take derivative of y to the 5th. Now, if you accidentally make the mistake of doing product rule on that, will you get the same answer?
Yes.
You will get the same answer. It'll just take you longer.
Isn't that how we prove that that's what you did? Doing the product rule?
Uh,
And calculate?
I don't.
Yeah, because if you do the product rule, then you just get the first chunk right there, and then
It's going to zero out.
Yeah, it's going to zero out.
Yeah. I don't think I didn't like prove that. I think I showed that it would happen that way, maybe. But. All right, we're done. Oh no, we're not. Sorry. Now we want to plug in 2, 1. Are we going to get the same answer?
No.
Not necessarily, right? We could, but it's not necessary that it happens. Because we're cutting it in a different direction. So our slope might be different in that direction. All right, so we're plugging in 3, 1 squared plus 5 times 2 squared times 1 to the 4th. What is that? 23? 23. So if I walk in that direction, it's going to be a steeper slope, right? One of the questions that we're going to ask ourselves later is if you're on that function and you go out to this point, the question will be this: what direction do you aim in so that when you take that first step, it's the steepest descent you could possibly get? that there's no other direction you could point and get a steeper ascent. Like a maximum incline. Because, I mean, here if we compare these two, right, we would say, hey, look, if you point in this direction, right, you're going to get 23. That's steeper than 6. But later we're going to say, we're actually going to be able to find the direction that gives you the maximum incline, and then we can compute what that incline would be. And that seems like that would be pretty difficult, but it turns out to be kind of a trivial thing. And it's using what's called the gradient vector. That might be useful, you know, if you have some map of some surface, right? Like let's say you've plotted out like a mountain, right? You've got some mountain, this 3-dimensional mountain, and you want to get up here, and you want to get up there in the shortest path. The shortest path will be the path that takes you, that every step is the steepest ascent. So if you can imagine at every point as you move up this mountain, right, every step you take is going to take you up higher than any other direction would take you. Then that will be the path. So you can use that to actually find shortest path. Then you can also find the path that would take you around the mountain without changing elevation. Because then you want that to give you, like your step, to give you no change. So you want to know, where do I aim so that when I take my step, I get a slope of 0. And you can basically find a path around the mountain without changing elevation. Uh-huh.
The shortest distance.
Yes.
Obviously, in real world scenarios, they would be different for each point on the mountain that you're going.
Yeah, your starting point would matter.
How would you, like, you know, do you just get that and then you compare the length of each one, or?
No, you're using the idea that the gradient vector tells you which way to point, right? So that you get the steepest ascent. So let's say it tells me to point this way, and then I take a step, right? Then I've gone up further than I could go in one step in any other direction. Once I get to that point, the gradient vector, I can compute the gradient again. And then it's going to say, now go this way a little bit. And I take this step, and then the gradient vector again. And what we can do is basically turn the gradient into a path, and that will lead us up the hill.
So then how would you consider each starting point? Like, which one would be the best? Because obviously, like you said, the starting point is going to matter.
That would be that's a different type of problem, I guess, because what I'm describing is you're starting here, you want to get there, right? Shortest path. Now, if you want to compare all the points around and find which of those points would give you the shortest path, that's a different, that'd be a little bit involved. Yeah, I'm pretty sure we could do it, but it's not something we would do in here, for sure. But see, in the real world, I mean, you know, the only reason you're going up a mountain is to probably in some military operation, and your shortest path is probably not important. It's probably getting there without getting killed or something, right? Okay. All right, how about that one? I would just say, hey, why don't y'all try this? But this one's a little more involved, so I think we should work through it. So I'm going to first try and find the partial of f with respect to x, which means I'm treating y as a constant. All right, what do we have going on here? We have chain rule, right? Because we have sine of something. And then within that chain rule, we have a quotient rule. So we have to kind of start out from the outside and work our way in here. So what is the derivative of sine of anything? It's cosine of that anything, right? But then chain rule says times. Now I need to take the derivative of what's inside. And that's going to be where I need a quotient rule. Quotient rule says derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. You might have learned that in a different order, but we should all get the same answer here. What is the derivative of the top with respect to x? That means treating y as a constant. It's just going to be y, right? So we have y, that's the derivative of the top, times the bottom, x squared plus y squared, minus, now what is the derivative of the bottom with respect to x? So it's a sum, right? So I just do them individually. Derivative of x squared is 2x, plus derivative of y squared is 0, because y is a constant. So this is just minus 2x times the top, xy, all over the bottom squared. So x squared plus y squared squared. That is not x to the fourth plus y to the fourth, right? All right, okay, close my parentheses here. That's it. And you could clean that up, right? Like you could distribute through and maybe things cancel and who cares, right? That's it. Let's move on to the next one. Partial of f with respect to y. All right, same story, right? Sine of something, so we take the chain rule, take derivative. It's going to be cosine of that something. Times, now quotient rule again. It's just that some things are going to change in my quotient rule, right? What is the derivative of the top with respect to y? X, right? X is a constant, y is the variable, so you just ignore the x. Derivative of y is 1 with respect to y. Then times the bottom. Yeah, and then minus, now derivative of the bottom, 2y times the top, all over the bottom squared. Are these the same answer?
No.
They look pretty darn close, but they're not, are they?
No.
They look a little bit off.
The x, one's an x, one's y.
Yeah. Okay. All right, you were asking about notation. So suppose you have z is equal to some function, so z is equal to some function of two variables x and y. Then the following are equivalent. And mathematicians like to write this instead of the following are equivalent because we're kind of lazy. You might see that in a textbook later on if you're like a math person. The following are equivalent. And it means that all of these are equal to each other, all right? So this is the notation I gave you, right? Partial of f with respect to x of xy. But that's the same as me just writing f with a little subscript x. So if I'm comparing this to Cal 1, this is kind of like me writing f prime of x. Okay, that's what that's kind of like. This is kind of like me writing f prime. This right here is kind of like me writing, no, this one would be df dx in Cal 1. This one would be dy dx in Cal 1. But notice this symbol right here. This right here is not the same as this. So we have a way of distinguishing between derivatives and partial derivatives. And we use this little, y'all know what that symbol's called? It's del. A lot of times it's called del. All right, but it's Greek lowercase delta.
And then like capital del is the triangle upside down.
Yes. So that you've seen delta. Change, capital. That's capital, lowercase. But the thing is, it's not the same as here. Here it's d, like the lowercase letter d, dy dx, df dx. Here we use this to this kind of lets you know that, hey, there are some other variables involved that we're holding constant. It's a partial derivative. You could also just put the partial with respect to what variable, the thing you're holding is the variable, not the thing you're holding constant, the variable, and then say, hey, I'm going to take the derivative of this thing, partial derivative of this thing. This notation in Cal 1 was d dx of f of x. And then this right here, I don't see this used a lot, okay? But F1, I don't really have a similar notation for this from Cal 1. I'll explain what F1 means in a second. D derivative, right? Derivative, subscript 1 of f. This one, capital D, derivative of f with respect to x. All right? Let's talk about that 1. What do you think f2 would be, or d2f would be in this circumstance here? No, not the second derivative. It's the derivative, the partial derivative with respect to the second variable. So what is the first variable in this function? X. So this 1 actually means we're taking the partial with respect to the first variable. This would mean the partial with respect to the second variable. Get it? Okay. So if you have a function of 8 variables and you write, f subscript 7, that means the partial derivative with respect to the 7th variable, holding everything else constant. The ones that we're going to use in here, let me show you the ones we're not going to use, all right? The ones you probably won't see that much of, this and this. Everything else pretty much you'll see. So in differential equations, what? You see mostly this one?
Sometimes they use D1.
D1? Yeah.
D1 of the, they sometimes use.
Yeah, sometimes this? Okay. All right. Now, how do you notate, because y'all thought that f subscript 2 meant the second derivative, right? Well, so that naturally asks, how do you find second partial derivatives? And what's the notation for it? And there's lots of notations. Okay, so let's first start. If we wanted to take the partial of f with respect to x and then get that answer, and then take the partial of that with respect to x again, we would write this: f subscript x in parentheses subscript x. Or you could just write fxx. I like this notation right here. f11. Does that make sense that you would do 1, 1, first variable, followed by first variable again? How about this one? Partial of f with respect to x. When you're done here, take the partial with respect to x of that. This one, partial squared f, partial with respect to x squared. Right? And then this one's the same thing, but using z instead. Do you all know why this 2 is right here in the middle and this 2 is on the side? That means second derivative, but why didn't they just do this? Partial f squared over partial x squared. Why didn't they just do that? Yeah, you might think, that's partial. You might think that means this, which is not the same thing. What this means is take the partial with respect to x and square that answer. This means, well, that's bad notation. This means you take the partial with respect to x and then follow it up again with the partial with respect to x again. That's why they offset the 2, so that there's no confusion with this. It's not some weird voodoo thing that we like to do to just confuse students. It's so this doesn't happen. All right, let's look at partial with respect to y, followed by the same thing. fyy, f, 2, 2. It's a typo. Let me fix that now. This won't take me long. Done. F22. All right? And then these are the other notations. So if you want to take the partial with respect to x, and then after that the partial with respect to y, this is the notation. So we're taking the partial with respect to x first, right? First, and then with respect to y. Here is showing it in parentheses. Take partial with respect to x, after that partial with respect to y. So the way you read this is the one that you'll see me use all the time in here, is when you read this, you're reading it from left to right. So you're going partial with respect to x first, then y. So what that means is that you can take the partial derivative of a function with respect to x, right? And then that spits out some function. Why not take the partial of that with respect to y then, afterward? And what meaning does that have? Does it have any meaning? I don't know. Maybe it does, maybe it doesn't. We'll have to see. What do you think this second derivative like this had, you know, what does your gut instinct tell you that's going to give you? What did the second derivative in Cal 1 give you? Velocity. Yes, that's if we have position and all that. But in terms of geometry, first derivative gave us slope of tangent line. What does second derivative give us? Concavity. Concave up or down, right? That's kind of what this is going to tell us too, is whether or not, you know, we're slicing that surface and we have a curve. That first partial derivative gives us the slope of that tangent line. The second partial derivative gives us concavity. All right, and then finally, last one there, partial with respect to y followed by x. So we got a function here. And I've asked us to find all second partial derivatives of this function. How many second partial derivatives are there? There are only 4. There are only 4. What are they? fxx, fyy, fxy, and fyx, right? Those are the 4 partials possible. There's no other combinations we can create. So let's do this one first. Okay, first let's find the partial with respect to x. What's the partial of that with respect to x? 2x plus 0 minus 30 x squared y squared. Now, let's take the partial with respect to x of that again. So the partial with respect to x again would be 2 minus 60 xy squared. Are you all okay with these partials? I know, I mean, usually in my experience of doing this, I have like half the class is like, yes, this is obvious, and then the other half's like, I don't know what he's doing. So if you're in that half that doesn't know what I'm doing, just talk to me after class or just stop me and say, hey. All right, so we're done with that one. How about this one? fyy. So partial with respect to y first. What is it? 20y to the 4th.
Minus 20x third y.
Okay, everyone agree? Okay, partial with respect to y of that. 80 y to the 3rd minus 20 x to the 3rd. Everyone agree with that? Okay, those are good. Move on. All right, when we do the partial of f with respect, which one are we doing with respect to first here? X first. So we already did that, didn't we? That's it right there. So I'm going to take that and do that one with respect to y. So derivative of 2x is 0, right? Because we're doing it with respect to y now, so we're holding x to be constant. So 0, and then what here? Negative 60 x squared y. Okay, good. Now partial, we're going to do the partial with respect to y first, and then followed by x. There's your partial with respect to y. So fyx. So do this with respect to x. So hold y to be constant.
0 and negative 60.
So 0 and
Negative 60.
negative 60
Y X squared.
x squared y again, right? Or yx squared, however you want to say that. That's what you get? We good? Y'all notice anything?
Yeah, they're the same.
These two are the same. These two are the same.
Is that always
Yes.
gonna happen?
Question?
For the fx of y,
This one?
yes, when you carry the line squared, what happens to the square?
Okay, so when you're okay on this part, right? Derivative of that is 0?
Oh, I was looking at the wrong one. I was looking at fx of x.
This one?
Yeah.
Ah, okay. So we're going back to this one. Got it? So the question, is that always true, right? Are these always the same? Not always, but we have a little theorem here. Clairaut's theorem. The question was, is this always going to happen? Are these partials, partial with respect to x followed by y, is that always the same as a partial with respect to y followed by x? And Clairaut's theorem says that if you're given a function of two variables, if f is defined on a disk D that contains the point x naught, y naught, and these partials are both continuous on D, then they will always be the same. Okay, what? All right, this is all this means. Do you remember with functions of two variables, you have the domain that's on the ground, right? And then you have the surface that's up here. This is saying that this is our z equals f of xy up here. It says, if f is defined on a disk that contains the point x naught, y naught. So let's say that we have a point down here, and that's the point x naught, y naught. And imagine that we create a little disk around this. Like a little circle, right? And we take this, and we take that little circle, and we map that. This is our disk, D. And we map that whole thing up here. It's going, well, the point's going to go somewhere, right? The point's going to go to a point. But then that circle is going to go to something up here, right? It may look like a circle. It may look something like something else, right? So as long as our function is defined on that disk, so we don't have any holes or breaks or asymptotes or anything happening in this little blue region, and the partials, when we take the partials, those partials are continuous, which means they don't have any problems with them inside this disk, then they're guaranteed to coincide, to be the same values. So the answer to the question is sometimes. They're the same. This is not something that I'm going to test you on or something. It's a theorem. It's just to answer the question.
Is there a set size that it is used to be?
Any size.
So it can be infinite?
You want it to be, as long as you can find one. So infinitely small, there has to be a radius to this disk. It can't have a radius of 0. Then it's a single point. So when we say a disk, it can be any size radius. So as long as we can pick a radius and all those conditions are held, then those are going to match. But if you can't find a circle around it where those hold, then it's not going to work.
So, in other words, it would work on the edge of the surface.
Well, it could work on the edge of a surface if your function has to be defined, right? So I'm trying to think of one where we would have an issue here. Yeah, how about this one? We have to be able to put a ball around, not a ball. We call these balls later, even though that doesn't look like a ball. I'm gonna look at this one right here. We did this one, I think, in class before. This one was that top half of the sphere of radius 3. if we went to the edge, so if we looked at the domain of this one, when we got the domain, it was a circle. The domain, circle of radius 3. So what would happen at the edge of this? I'm going to leave that as an open question for you. I think you can figure that out yourself. What would happen if you pick a point on this edge? Will this hold? Understand what you need to do? Okay. The theorem says you have to be able to create a ball around it. I said ball again, didn't I? Okay. I may as well explain it. Unit balls. Okay. In R1, the unit ball is, it looks like this. R1 is a number line. Here's 0. Here's -1. Here's 1. It's all the points that have a distance of less than or equal to 1 from the origin. So a unit ball on the number line is that little interval, closed interval between -1 and 1. That's a unit ball in one-dimensional space. A unit ball in two-dimensional space is going to be a circle of radius 1. And it's everything inside and including the boundary. That's a unit ball in 2D. In 3D, that's a unit circle, right? In 3D, it's the unit sphere, right? Three-dimensional. It's everything inside and the edges. How about in R4? It can't, right? Well, okay, let me try something here. Do you agree with this, that this is saying that the absolute value of x has to be less than or equal to 1 here? And isn't this one saying x squared plus y squared, that has to be less than or equal to 1? Isn't that what this is saying? This is a circle, right? If I turn that to an equal sign, that's a unit circle. But if I say less than or equal, it's the circle and everything inside of it. Okay? What is this one saying? X squared plus y squared plus z squared has to be less than or equal to 1. And if I come back up here, isn't the absolute value, I mean, couldn't I do this? Like, I could change this equation over, couldn't I? And this would give me the same thing? If I say x squared is less than or equal to 1, won't it give me the same thing here? Yes? Okay, so what does the unit ball in four-dimensional space look like? Yeah, I can't draw it for you, but what I can tell you is that if you have the 4 variables, I can tell you that if you take the sum of missed a squared. If you take the sum of the squares of the 4 variables, that inequality must be true. It's all the points in four-dimensional space that satisfy that inequality. So on and so on. And there's actually unit balls in infinite dimensional space. There is such thing as R infinity, which is like R1, here's R2, R3 is 3. You can have infinite dimensional Euclidean space. But I'm digressing. Okay, let me get back on task here. Sorry. That's interesting. I don't know why I called it a ball. I haven't used unit balls in a long time. I think I'm just getting old. I think that's what's happening. One day I'm gonna walk in and be that professor that's up here talking about, man, tell you what, back when I was a kid, and like 30 minutes in, and be like, what was I doing? What are we, calculus 3? Well, if we can have second partials, why not have third partials and fourth partials? Right? You can just continue following up with. Now, these don't actually have a whole lot of meaning in terms of, like concavity or anything like that, but mechanically, it's something we can do, right? And do you remember